Hi, Professor. So now I'm going to talk about our project too. So according to the project, we're going to build a full adder for one bit full adder for the project. So in Fortisprite, I have built a full adder here. So it requires two AND gate, two XOR gate, and one OR gate. So after combining it, this is my full adder. So we have two input A, B, and one carry here, C carry in here, and one carry out, and one output S here. So to test the efficiency, to test the functionality of this circuit, we have to do a waveform. So this is the waveform I've done. We run the circuit. So this is simulation. You can see this is correct. 0 plus 0 plus 1 is 0, 1. 0 plus 1 plus 0 is 0, 1. 1 plus 1 plus 1 is 1, 1 in binary. So we can conclude that this is correct. So after we've done this, in the project we need 4 full adder to achieve 4-bit adder or subtractor. So so we'll make this into a symbol. So to achieve this, we have to open file and create an update and create symbol file for current file. So we have to add save. So I've done this before, so I have a symbol here. So now I don't have to save it. So after we do this, we have a symbol and the schematic here. So we can use it in the new project, and we can create a new component there with the function, with the same function here. It will be easier for our work. So I'll show the step later. So the next thing we need to do is the 4 to 1 multiplexer. So to make a 4 to 1 multiplexer, we need four 3 input AND gate, one 4 input OR gate, and this only. And we have 4 input, and each input represent one possible output and 2 selector. The selector will select the output needed from the input. So to test the functionality of this circuit, we have to open the waveform. We can simulate the circuit. So in this simulation, we can see that when selector is 0, 1, the output Q is A1, 0. So when the selector is 1, 0, the output is 1, same as the A2. And when the output is 1, 1, when the selector is 1, 1, the output is same with A3. So we can conclude that the multiplexer function well. So according to the project, we also need 4 to 1 multiplexer to achieve 4-bit multiplexer. So we will do the same thing like the adder. We need to create an update and create a symbol file for current file. And same thing, I have done this before. I have saved this before, so I have the symbol here. So I will not save here. So the next thing, we have to open the project. So from the file here, we tap into full adder, the project file for the adder just now. As you can see, we have the full adder symbol and the circuit. And the multiplexer here, we have the symbol and the circuit. So what we have to do, we have to copy the symbol and the circuit of both of this component, and we have to paste in the new project file. So now we're going to create a new project for the combine the project. But actually I've done all the project, but now I just have to show you how I add the component of the adder and multiplexer. So I select here, open a new project, and I will open a new folder, new project, select folder. So add a name for the project. Next. So this is now we need to copy the symbol and the schematic. And the adder. So now we've copied, and we're pasting in a new folder. So we have to add the thing. And now we have to add a name, multiplexer 4 to 1, 8, and a full adder. 8. So next, so there's nothing for us to do. So now we can see a new schematic file. So now we tap the symbol project, and we can see the full adder here. So we can put the full adder, 4 full adder to make a 4-bit adder of subtractor, and a 4 multiplexer to achieve 4-bit multiplexer. Yes. So this is how we do. So this is how we compress the file into a component and use it in a combined project. This will simplify our work. So now this is our full completed project. For firstly, we got multiplexer here. We got 4 to 1 multiplexer to create 4-bit multiplexer. We got 4 inputs here, A1, and we use bus line, so I can separate the inputs here. For example, I got A00 here, A01, A02, and A03. And for A1, I have A10 here, A101, A102, and A103. So the function of bus line is so we can simplify the input. We don't have to put so much input, but we can edit the input. We can separate the input. So here we got B, for the multiplexer for B, the function is same with A. And the output A will go to the full adder. We got 4 full adder here to create 4-bit adder or subtractor. So it comes to the A input here. And for B, we got a XOR gate here and a ALU operation here. So based on the project, when the ALU operation is 1, the full adder will act as a subtractor. When ALU project operation is 0, it will act as a adder. So it will so this input and the input and output from the multiplexer B will come into the XOR gate. So when ALU operation is 1, it will toggle the output from B. For example, if ALU operation is 1 and the B output here is 1, the output of the XOR gate will be 0. So but if ALU so this XOR gate will act as a NOT gate to change B into the two complement. Yeah. So when ALU operation is 0, it will not affect the output. So the output from B will directly go to the adder. So from here the adder will combine, will add A and B, and the ALU operation will connect to the first full adder to C in. So when it is subtractor, the C in should be 1, and if it is adder, the C in should be 0. So here we have the output from the full adder, S0, S1, and S2, and S3. We got 4 output here. Each output comes from each full adder. We can check the output here. We can check the result of the full adder here. And next, we got the register here. We can find the register from the component here. Primitive, I think, buffer. Oh, yeah, storage. We can find the register D flip flop here. So in the flip flop, the output from full adder will connect to the D input here, and a clock and reset input will connect to the register also. So the clock is used to the output will only change when the clock is going up, and other time the output will not change. And when reset is low, the output here the ALU output will be 0. When reset high, the ALU output will change. Yeah. So if the reset is high, all the ALU output here, ALU output 0, ALU output 1, 2, and 3, supposed to same with the S0, S1, S2, and S3 here. So to see the function of this circuit, we can open the waveform and see the simulation. So in this waveform, I've set all the input differently, so we can see the variety of output. And the clock I set a small time, so we can look small output here when the clock is going up. I've set all 1 first to see the output of ALU. So now we run the simulation. So in this simulation, we can see. So with that clock, we see when ALU input is 0, so it acts as a adder. So here selector A is 1 1, so A3 will be selected, and selector B is also 1 1, so B3 is selected. 1 1 1 0 plus 1 1 1 0, it will become 5-bit 1 1 1 0 0. But here we only cover to 4 bits, so we will get 1 1 0 0 for S. And for ALU output, it will be same with the S 1 1 1 0 0 S. The reset is high. So the next, selector A is 0 0, selector B is 0 0, A0 is selected, and B0 is selected. 1 1 0 0 plus 1 1 0 0, the outcome is 1 1 1 0 0. But this here we only have 4 bits, so we will get 1 0 0 0 and ALU as well. So to look at another example, so here selector A is 1 0, A2 will be selected 1 0 0 1, and selector B is 0 1. B1 will be selected. So 1 0 0 1 plus 0 0 1 1, it will become 1 1 0 0. So here the S output is 1 1 0 0, and ALU output is 1 1 0 0 as well. So if we see the output when the ALU operation is 1, it will act as a subtractor. So here when the selector is A, the selector A is 1 1, A3 is selected 1 1 1, and selector B is 1 1. B3 will be selected and is 1 1 1 1 as well. So when A subtract by B, the output is 0 0 0 0, same as the ALU operation. We look at another example. Here selector A is 1 0, A2 is selected 1 0 1 1, and selector B is 0 1. B1 will be selected is 0 1 1 1. So the output should be 0 1 0 0. Yeah, and the ALU operation no. So and the ALU output is also 0 1 0 0. So we can prove that our circuit is functioning. If you want to see the result when reset is equal to 0, so now we change back to the waveform and we change the reset into 0 and run the simulation. as you can see, now in this simulation, all the result is same except the ALU output is 0, 0, 0, 0 all the time because the reset is 0. Yeah, so that's all for me. Thank you.